So in the last class, we ended with some boundary conditions. Let me repeat a bit of this. So we said there are two type of boundary conditions. The first one is which comes on velocity, and other one of course will come from stress, but we will relate it to the velocity. So first we talk of the kinematic boundary condition, which is a boundary condition on the velocity on two sides of the boundary. What is a boundary? Where one fluid ends and on the other side there is either a different fluid or there is a solid. So it is the end of the domain. Okay. So now, or sometimes even when you cut a section, then it is at the cut section, the control surface, for example, would be a boundary. So even though there may be no physical boundary, but you are choosing a control surface, so that becomes the boundary. Okay. So now we said that in the kinematic boundary condition is that if we look at the velocity of the fluid at the boundary. Now the boundary itself could have the velocity also. For example, if it is a liquid gas interface, then the boundary may not be rigid. So there, when we look at the velocity, we look at the normal components of the velocity on the two sides and the tangential component of velocity on the two sides. And the boundary condition which we write is the normal components of velocity will be equal, and this one would expect from a mass balance perspective, that if fluid is going in, then the same fluid, it has to be seen on the other side. So this is sort of can be understood from a mass balance perspective. But we also impose a second boundary condition, which is that the tangential component of the velocities on the two sides of the boundary are same. Now, for this tangential component of velocities to be equal, this is a statement which we cannot prove. This is a statement of expectation. We observe, and this expectation comes because of viscosity. That is the role of viscosity, that if there are two layers of fluids, then they are clinging to each other, and the velocity, if I look at on one side of the layer of the fluid and the other side, that has to be the same. And this does not stay with only with the fluid. Even at the boundary, we expect the same behavior, that velocity on both sides will be same. And this is what we call as the no-slip boundary condition. Now, firstly, under some situations, this condition does not hold. The first one is, for example, if we have flow in a very thin channel, where on the surface you have coated a material which is called a hydrophobic material, which sort of repels the fluid. There what you will find is that in a case like that, the velocity at the of the layer of the fluid which is touching the wall will not be zero. It is something, it will not be very large, but it will not be zero. This is what has been observed in experiments also. And secondly, a second example one takes, which all classical textbooks give, is if you look at flow of liquid helium on a wall, then the liquid helium which is just touching the wall will not have a zero velocity. So these are exceptional cases, but when we analyze flows, sometimes we make the inviscid approximation. If we make the inviscid approximation, then we relax the no-slip boundary condition. There will be a reason for this also. If you realize viscosity, if you look at the Navier Stokes equation and the viscous term, then the viscous term has the second derivative. So if you are now relaxing if you are assuming viscosity is zero, that will means you will need one lesser boundary condition, because now the second order term is not being considered in the equation. So therefore, the relaxation of this boundary condition goes well with the mathematics of the problem. So in viscid flows, the viscous term is mu del square V. So, second derivative of V comes with this term. If this term is assumed 0, then the order of the equation becomes 1. Instead of 2, and 1 less boundary condition is needed. So, this is a term which is relaxed. The no slip boundary condition is a very usable boundary condition for a fixed wall. The velocity at the wall is 0. So, because this velocity is known, so it becomes a very usable boundary condition. That means, even when you look at the problem, without solving any equation, you should be able to say, okay, velocity at the wall will be 0, both the normal and the tangential components. So, in that sense, this becomes, for flow next to a wall, this is a very usable means. When you solve the equation, you will have to apply the boundary condition, as you will see. So, then you can use this. So, this was the first type of boundary condition. The second boundary condition which we have is on the stress. So, we call it the stress boundary condition, and again this is fluid 1, this is fluid 2. Let us say this is point A, this is point B, and the stress boundary condition becomes normal that normal and tangential components of stress are equal at A and B. Now, again, as I said, the tangential component of stress is equal if you make a small element on the boundary. So, you can derive this by considering so if I consider a small element on the boundary and then do a force balance, then the force balance will tell us sum of forces is equal to mass times acceleration. But then what will happen is, because mass is a volume term and the other terms on the boundary, when you look at the boundary forces, will contain area, in the limit that this extent of this becomes very thin. the volume terms go away. So irrespective of acceleration, we get this, that the components of forces and that leads to stresses will be equal on both sides. So now, how do we use this? And in order to use this, let's have a look at our constitutive laws. So to use this, and we will see how or examine so for example, if I look at it, we get sigma xx is equal to minus p plus 2 mu now this I have copied from the handout. I don't remember this. I don't expect you to remember this. So I get sigma xx is equal to this. Now what we are assuming is we have solved the Navier Stokes equations. If we solve the Navier Stokes equations, what will we get as an output? Pressure and velocity. So pressure and velocity we know. So now when I say sigma xx is equal on both sides, then I will get minus p plus 2 mu partial Vx by partial x minus 2/3 mu del dot V will be equal on side A and side B. Okay. So now when I use this, if it's an incompressible flow, del dot V will be 0. So this term anyway becomes 0 for incompressible flow. So what you will get is, when you try to use this, minus P plus 2 mu partial Vx by partial x calculated on side A is equal to minus P plus 2 mu on side B. When we equate the stresses, this is what we will get. Similarly, I can equate the y stresses and the z stresses for the other directions, and that is what I will get. Now what you will find is, in most of these situations, even partial Vx by partial x will be 0. When you find the solutions, as we will see them, otherwise you are supposed to equate them. And this often in many cases, this will translate we get, I can maybe in many cases I would say. And thus the stress boundary condition becomes pressure on side A is equal to pressure on side B. Because if the other terms are all 0, this will just become pressure. And this in particular but this one has to remember, this works in the absence of surface tension. If there is surface tension, then there is a normal force which is caused by surface tension, that also has to be included in the normal forces. So this is in the absence of surface tension. हम नहीं करेंगे. So in the absence of surface tension, we will have this. Now similarly, we look at the if we look at the shear stress boundary condition, so let's look at one of the components. We have tau xy. This comes out to be equal to mu times tau xy, which is also equal to tau yx, is mu times partial Vx by partial y plus partial Vy by partial x. So this one has to then equate that. So now whenever you solve the problem, to be able, what you will find is that you will get some unknown constants when you solve the differential equation. And to solve those constants, you will need the boundary condition. So this is what you get when solve NS equations get some unknown constants. We need them. Maybe this should have been the starting line when I talked of the boundary condition. The motivation would be this, that when we solve the Navier Stokes equations, we get the constants and we need the boundary condition. So now coming back to the shear stress boundary condition, this will give us mu times partial Vx by partial y at A this is for a fluid boundary. On the boundary where there on both sides you have fluid, then when you equate the shear stresses, you get this. Now you see, I am not using Newton's law of viscosity, which we used in the first lecture on fluids. The reason being, now I have a general expression, so I will use this. And this equation will give me then, so we will have this thing. Now what happens is, there is a particular case, if it is a fluid solid boundary, then what you will have is mu partial Vx by partial y Now, on the solid side, you cannot write this expression that is valid for fluids only. So, if it is a solid fluid boundary, what you will get is tau xy on the solid side is equal to mu partial Vx by partial y plus partial Vy by partial x on the liquid side. Now, from here you can realize that this boundary condition, thus for a fluid solid boundary is when I said that in most problems we first look at the boundary conditions, so you think of boundary conditions as an input to the problem. But when we have this on a solid surface, then what you do is you solve your velocity field, which will assume you can get all the other constants from other boundaries. And then what you will get is this will give you the shear stress on the solid side, which is what you want to get as an output. Because you integrate that to get the total force, which is the tangential force acting on the solid. So in that sense, this boundary condition is not a usable boundary condition, but it is an output which you need from the solution. You solve and you use this to get tau xy, and then you integrate that to get drag force or lift force or moments, whatever you need. So this will be used more as an output on a solid fluid boundary. But if we look at this, but this is a usable boundary condition on a liquid gas interface. That means, let's say there is gas here, there is liquid here. This boundary condition will become mu liquid times you will solve the equation separately on the gas side and the liquid side, and when you apply the boundary condition becomes like this. So here then what happens is, let's see, so this we can write it as partial Vx by partial y okay. All I have done is taken the mu on the other side, and there now we use, what we find is, and if you remember in the last class I gave you the numbers for water and air, and we found that viscosity coefficient for water was about 1000 times the viscosity coefficient for air. And in general what we find is viscosity coefficient for gas is much less than viscosity coefficient for liquid. So if mu g upon mu L, this is equal to epsilon, and epsilon tends to 0, then what can we say about the velocity gradients on the liquid side? So this will lead to and what one observes is the gradients in the liquid and gas sides are actually not very different. So therefore, this boundary condition translates to the shear stress is 0 on a liquid gas boundary. Therefore, the shear stresses by themselves will be a very small order of magnitude, because the velocity gradients on both sides, liquid side or gas side, the velocities are anyway equal and the gradients don't vary that much. So therefore, the shear stress itself on the boundary where we have highly varying viscosities is nearly 0. And this becomes a very usable boundary condition, because then you will say if there is a liquid gas boundary, on that boundary shear stress will be 0. So this is how one can then work out. So this becomes a usable, I have already written this. Is that clear? So now what we have seen is two types of boundary condition. If it's a solid, then the velocity there is equal to the velocity of the liquid. And now what happens in a liquid boundary? There all you will say is mu A partial Vx by this thing is equal to mu B times that. And then you'll have to go to the other fluid, solve the equations in the two fluids, maybe on the two liquids on two sides, on both sides there may be solid. So use the solid boundary condition in liquid 1 as well as liquid 2. So this is what you may have to do. And on this interface you'll have to equate. Now, so therefore what we have is, I'll just take another minute, on a, pardon? लिखवा चुके हैं, but उसमें what I wanted to tell you was that the velocities are also equal and the shear stresses are equal. So therefore when we analyze this, what you will get is partial Vx by partial y on A is equal to Suppose there is only Vx. So that means also we have Vx at A is equal to Vx at B. So what this will imply is velocities are continuous. But the velocity derivatives on a liquid-liquid boundary the velocities are the same, and because shear stresses are the same, and if the viscosities are not equal, then obviously the derivatives will not be equal. So there is a discontinuity in the derivative, but not in the velocity. That is what I wanted to emphasize here. Okay. That fine? So next, so we have seen how to deal with the boundary conditions. Next, what I'm going to do, and this is a part which at least some of you may find very interesting, is how do we solve the Navier Stokes equations? Let us have a look at that, and that is what we are going to do in some bit of today's class. In the tutorials, I have asked the teachers, they will do the workbook part till this differential equation. That will be the next 2 weeks. There's one on mass balance that is very simple, and the next one is differential equations here. And you can also start looking at, there are 4 or 5 workbook problems with fill in the blanks. So after today's class, what I'm going to do now, you can start solving those problems yourself also. Okay. So first, let us now look at what we call as exact solutions of Navier Stokes equations. And when I say Navier Stokes, continuity is always inbuilt in that. So that means we start with this. And we try to obtain analytic solutions for V and P by solving the Navier Stokes equations. Now, exact solutions known only if V and P depend on at most we have 4 independent variables. If velocity and pressure depend on at most 2 of them, then only in some cases, not all cases, you can find these exact solutions. So therefore, we have to make idealizations to solve the equations. So what type of assumptions do we make? One assumption is steady versus unsteady flow. And often you will find we will make the assumption of steady flow, which means V and P So we make this assumption that velocity and pressure do not depend on time, and we will say it is steady flow. In a lot of situations, we talk of two-dimensional flow, and if we say two-dimensional flow, that is planar flow, in x and y directions, it's in the xy plane. So actually the flow will also be in the z direction, but if that direction is large, we will assume that things are not changing with z. So we have a two-dimensional flow. So in two-dimensional flow, if it is in xy direction, Vz is 0, and any quantity will not change with z. Then the third simplification which comes is in flows with circular symmetry, where we use r theta z coordinates, if we have axisymmetric flow, this implies things do not change with theta. There is a circular geometry, so the velocity, pressure, they may not change with theta. V theta may or may not be 0. We could have a case of flow around a spinning cylinder. So if the flow is about a spinning cylinder, V theta will not be 0. But still, if it's around a cylinder, things may not change circularly with respect to theta direction if there is a circular symmetry. And that is what we call as axisymmetry, and this simplification is often used. The next thing what we have, and this is the key one which we will use, if, so are these three things clear? Steady, unsteady, you start a flow, immediately at that time flow will be unsteady. But after some time, once the flow is set up, things don't change with time, if you're not changing anything at the boundary with time. So then secondly, I talked of 2D flow, and then I talked of circular flows, circular axisymmetric flows. Now the fourth assumption which we make is, or if one flow dimension is much larger than the other. Let me first give an example. Flow in a long pipe. Let's assume fluid flow through a long straight pipe. That means the geometry of the pipe is not changing with this. So here if this is the z direction and that is the r direction, then if this is L, if the radius is r, so then this will be 2r and this is L. Then if pipe is long, L is much greater than r. Or if we have flow between two long plates, we call this as a channel flow. So let's say this is 2H, this is L, if L is much bigger than H. So in this cases, we idealize L as infinity. Because L is very large, we idealize this to be infinity. Now what happens is, if L is infinity, then does it matter at which point do I place the coordinate system along L? I have placed this coordinate system here. Suppose if I take it to slightly to the right or slightly to the left, will it make a difference? If this direction is infinite, I can place the coordinate system anywhere along that location on this axis. So here, if this is so, then we can place, let's say L is the x direction. So we can place the coordinate system anywhere along x, and the flow should not change. So what this will imply is that if the flow will not change by shifting the coordinate axis, the derivative of velocity with respect to this big direction will be 0. Okay. Now I am not using pressure here because the flow may be caused by the pressure difference between the two ends. So if it is caused by pressure difference between the two ends, I can't make this assumption for pressure. But for velocity, we can say that along that long direction, the flow will not change. So x is the large length direction. So for pipe flow, x will become z, because we had r theta z, I called z as the large direction. So we have this, and this is also called a fully developed flow. That means possibly near the entrance and the exit, this condition may not be valid. But during the most of the regions, this will be valid, and that is why you say fully developed. And you can also think of it as analogous to time for a steady flow. When a flow starts, it is unsteady, but it sets up and then with time it does not change. The same thing is happening in the very long direction. That when at the entry, maybe it takes time to adjust the profile, but once we have reached some distance, after that the flow does not change with the long direction. And this is an idealization which is made, and this sometimes is called the fully developed flow. Now the same thing will happen in this channel. I have taken this as a 2D flow. But suppose if the z direction is very large, this is the direction coming, then partial v by partial z will also be 0. Not just partial v by partial x, both of them will be 0. And that's why we make the two-dimensional approximation. So these are some of the idealizations. Some of them will be stated a priori, but otherwise you have to make some of these assumptions in the problem. And this is what, at least parochially, I call it as converting English into maths. If I say flow is steady, you have to think partial by partial t is 0. Flow is fully developed fully developed means you look at the major velocity in that direction, the flow is not changing, so it means partial v by partial x will be 0, and so on, and then we will solve. So now Given this, let's try to start solving the problems. And the first problem which we will do is flow in a long channel. So we assume the problem statement is it given two-dimensional flow in a long channel caused by pressure differential between the two ends So this is the channel. We set up our XY coordinates like this. Pressure here is P1, pressure here is P2, this is 2H, this length is L. So this is what the problem is specified. Then it will be also say assume steady 2D flow and L is much bigger. So we are given the two pressures, we are given that the flow is steady, we are given its two-dimensional flow, and we have to solve now. Given this equation, the problem says find the velocity and the pressure distribution of flow in the pipe. Okay. See, this is how now we are doing the differential flow analysis exact solution. In the other version, for example, if it was an integral flow problem, then possibly the velocity or the mass flow rate would have been given. You would have been asked to find what is the total force the flow is exerting on the pipe wall. The same problem can be posed in the differential, in the integral flow format also. Okay. So we will see the differences between the two just after we solve the exact flow. So let's start with this. So firstly, in all these problems, let us start with the boundary conditions. So boundary conditions at x is equal to 0, p is equal to p1, x is equal to L, p is equal to p2. These are the boundary conditions on pressure which are given to us. What are the boundary conditions on velocity which we can have a look at this problem and get directly? Can you please tell me? Now this is a two-dimensional flow, so we have to solve only for Vx and Vy. Do we know Vx and Vy at the boundaries? Zero. Both on the boundaries, that means, so see now, you see how I am solving the problem. I am starting with the boundary condition. I have not looked at this equation at all. These big equations, I am not looking at it. So on the boundary, what I get is that y is equal to, and I put both of these together, plus minus h. Vx is 0 and Vy is 0. Suppose if this was a porous wall, one of these walls was porous, then what could you have, what would be the boundary condition there? If the wall had holes, it was so there, if you look at the wall and the flow can seep in through the walls, so Vy will not be 0, Vx will still be 0. Vx is 0 because of the no slip boundary condition. So if these were porous walls, then Vx would have still have been 0, Vy would not be 0. It would have to be specified by the whatever is the pore flow rate or whatever. Okay. So this is the type of things which you have to see in the boundary condition. There may be different boundary conditions in different problems. So then what we have is, let's try to analyze. We are solving for Vx and Vy. And to start with, now this is an analysis you have to do in your head. You don't have to write this. But because this is a 2D problem, so things are variables are functions only of x, y, t. Now, does any variable go away? Will it not be? Now, given these assumptions, t goes away because of steady flow. Okay. Now, what about any other way? What can we say about Vx and Vy as functions of x? Will they be functions of x or not? So we can then also put in a reasoning. So not function of t because of x direction is large. This implies partial Vy partial x is 0. Obviously, pressure is a function of x. It is given to you in the problem. There is P1 and P2 which are not equal. Okay. So that means what we get from here is, if this also goes away, Vx and Vy are only functions of y, and pressure could be a function of x and y. Is that fine? Now we start to simplify the equation. So we have got all these things. So then the first equation we move on is always the continuity equation. First we will simplify the continuity equation, then we will come to the Navier Stokes equation. Now what is the continuity equation? Continuity equation, please take your sheets out, and now you will require your sheets. Continuity equation means del dot V is 0. Where is that written? It is written in the center of the page, B8. And incompressible flow, so forget all densities. So continuity equation leads to okay. Now can we simplify this? Is any of these terms 0? The first term is 0 because Vx is only a function of y. So this becomes so I make two more simplifications. First, I reduce that term. Secondly, I convert this partial derivative to a total derivative because Vy is only a function of y. Now, can I solve this equation? If partial Vy by partial y is equal to 0, this will imply Vy is equal to constant. Now, can I use the boundary condition? Vy is constant for all y's, but I know at y is equal to minus h or plus h, Vy is equal to 0. This implies Vy is equal to 0 for all y. So that means in this flow, Vy is 0 everywhere. Is that clear? Okay. That is the boundary condition which we wrote here. Okay? पूछ लिया करो. ऐसा कोई भी doubt है, please don't hesitate. Ask these doubts in the class. Okay. So next thing what we are going to do is, we will move on to the Navier Stokes equations. Now we have two equations, x and y. Okay. So which equation should I attack first, x or y? Actually you can attack any one, but because we have some simplification for Vy, that it is 0 at all points, I think it will be easier to use the y equation first. Because we already know most of the terms will there become 0. So let's look at the y equation first. So y equation for momentum. Let's look at that. So now I am going to my handout and I will write the equation first. So, well, I remember it, at least the xy version. So partial Vy by partial t plus Vx I write this equation. Now let me start making terms 0. Which all of these terms are 0? This is 0, the steady flow, this would have been 0, but Vy is also 0. Now this term, Vx is not 0, but Vy is not changing with x. So this second term is 0, so this also becomes 0. Now in the third term, this is Vy by partial y, sorry. Now this becomes 0 because of continuity equation. So this term is 0 and both of these are 0. So now here again both of these terms are 0. So even one of them 0 would have made it 0. Now partial p by partial y, let's say, stays, plus g sub y stays. Now let's look at the other terms. Mu times, now because Vy is 0 for all y, all of these become 0. See, it's not because of the boundary condition, but it is because Vy is 0. So therefore, this equation then boils down to, there's a row here, so now suppose if gravity is acting in the y direction. Now the way we have specified the pressure is P1 at the inlet. That means we are not considering the variation of gravity with pressure. This pressure is so high that the gravity effects are negligible. So that means in this case we can basically assume G is equal to 0 because pressure is equal to P1 for all y at x is equal to 0. So we have assumed this. So we get is partial P by partial y is equal to 0. This is the simplification of this equation. Now maybe if it is an exam problem, I will also assume G is equal to 0. I will not let you get confused with this. So I'll put that. But now we have partial P by partial y is equal to 0. Either we can leave it here or we can go one step further. How can I integrate this equation? If I integrate partial P by partial y is equal to 0, what do I get? P is equal to constant or what? This is a partial differential equation. So if I integrate this, this will imply P is equal to some function of x. It will not be a constant, it will be some function of x. And that is what we can get from here, that P is equal to some function of x. Okay. So now, once we have done this, or if you put it in this form, if in some problem, if g is not given as 0, if gy is equal to minus g, then you will get P is equal to minus rho g times y plus f of x. If gravity is not to be neglected, then you will get this. Now, the information which you need from here actually is what is partial P by partial x, because this will come in the x equation. So we can if I get to partial P by partial x, I get partial P by partial x is equal to f prime x, and this is valid even if gravity is there. It is not a function of gravity, so we get this. So this is the take home from this equation. We can't do anything more. So then we move to the x equation. So far what have we solved for? Vy we have solved. Pressure, only thing we get is a function of x. And for Vx we have not solved anything. So now let me write the x equation. So this is rho times partial Vx by partial t plus Vx I think you people should also write down so that at least you'll get a hang of it, how to do this. Now let's start simplifying. लिख लिया सबने equation? Has everyone written this down? Now you start simplifying. Now here we know Vx is not 0. But which of these terms are 0? The first term, is it 0 or not? This is 0 because of steady flow. Okay. Now the second term, is Vx 0? No. What about partial Vx by partial x? This is 0 because of fully developed. So the whole term becomes 0. Now in the third term, what is partial Vx by partial y? Is it 0 or not? We don't know. It is not 0 the second term. But the first term, Vy is 0. So this comes from continuity equation, Vy is 0. And in this, both of these are 0. So whole of the left hand side becomes equal to 0. Now in the right hand side, we have minus partial P by partial x. So this is equal to f prime of x. So 0 is equal to minus f prime of x. G sub x is 0 if gravity is vertical. Now what about the viscous terms? Which terms stay? Or do all three are 0? Y and Z are 0. Vx is, एक मिनट चलो, let's see. Vx and Vy are functions only of y. So which terms will be 0? X and Z derivatives. Because this depends only on y. So from here what we get is, this will be 0 and this will be 0. Okay? So what we are left with is plus mu And this I will write it as equal to, you can do it in one step. I will write it as, now I change this to an ordinary full derivative because Vx is only a function of y. So what I get is d2 Vx by dy square is equal to f prime of x by mu. Now, left hand side is only a function of y. Right hand side is only a function of x. So when can that happen? So when this is a constant. See, a function of x I say, so this is a function of y. Right hand side is a function of x. So if a function of y is equal to function of x, this implies at best this is a constant. And let us call this constant as this f prime x was nothing but the derivative of pressure with respect to x, so I call it as p prime of x by mu. Now, this p prime is nothing but equal to, because this is a constant, so therefore this p prime was derivative of pressure with respect to x, so that will be nothing but p2 minus p1 divided by L, because it's a constant. Otherwise it could have been some function, maybe it had some functionality of x times x plus ax square plus bx plus c, but because it's a constant, then p prime will be equal to p2 minus p1 by L. कैसे निकालेंगे? हमें p2 भी पता है, p1 भी पता है, L भी पता है. So that means we know p prime from the problem specification. So now let's solve. Pardon? Because p prime है ना, it is derivative of see, because that will come from this partial p by partial x is equal to p prime. So what is partial p by partial x? p2 minus p1 by L, because it's a constant. Otherwise it could have been some function of x. Once we show that it is a constant, then this f prime has to be nothing but p2 minus p1 by L. क्योंकि constant है वो, अगर constant नहीं होता तो we could not have said that. Okay, so now can we integrate this equation? d2 vx by dy square is equal to constant. Let's start integrating it. So that means dvx by dy will be equal to p prime x upon mu plus c1. We integrate it again. Vx is equal to p prime, sorry, I wrote x, it is p prime y है. ये ठीक करना पड़ेगा लेक्चर. Let me write this again. I have to integrate this with respect to y. So obviously this is equal to p prime okay. Now how do we find C1 and C2? And this is where we will go to the boundary condition. What we have is at y is equal to minus h, Vx is 0. At y is equal to plus h, Vx is 0. So that means 0 is equal to p prime h square upon 2 mu minus c1 h plus c2, and this will imply 0 is equal to P prime H square upon 2 mu plus C1H plus C2. So this will lead to C1 being 0 and C2 is equal to minus P prime H square upon 2 mu. And this gives us Vx is equal to okay. So this is what we get for the velocity profile. Now from here we can calculate the flow rate. Flow rate will be equal to Q dot will be equal to integral from minus h to x Vx dy into W, where W is equal to the width of the channel, the Z dimension. So this will become equal to you calculate this, you will be able to calculate the flow rate in terms of the pressure drop. Okay. Now this is a very simple example, but practically you can now use this to find the shear stress on the surface of the plate, and that is the force which the flow is exerting on the plate. So we can also find tau xy at minus h or tau xy at plus h. This is the shear stress on the plate. Now, if we have a situation like this, so we have solved this problem. All these equations which look very big, with these simple assumptions, we can find a solution. Actually, it turns out that there are very few problems for which we can find solutions like this. And almost all of them, you will solve them in examples. Okay. But now, suppose you have a situation like this. I'm talking of flow between two plates. If the pressure at the two ends is equal, how can we cause this flow other than by pressure gradient? We have flow between two plates and there is fluid in between. How can we make the fluid move if given we are not able to create a pressure difference? Is there some other physical mechanism by which we can make the fluid move? The only other mechanism will come if we move one of the plates or if we move both the plates. If we move the plates, then also the fluid will start to move. So we can also cause this flow by movement of the plate. So if P prime is 0 and velocity Vx at y is equal to 2h is V0, this will cause the flow. Now in this case, because P prime is 0, so d2 Vx by dy square will be 0. So what will be the velocity profile which will be there? It will be a linear profile because second derivative. So here what we get is, when we look at the velocity If the bottom plate is fixed, we get a linear velocity profile if P prime is 0. And this flow is called Couette flow. Now, if this gap, instead of calling it 2h, I call it as h. I called it 2h because of the symmetry in the previous problem. If it is like this, then the velocity profile just takes a linear form. Because at y is equal to 0, it is 0. At y is equal to h, it is equal to v0. So we get it. But to get to this linear form, we need to simplify the equations to be able to get this. Otherwise, we can't get this form. So, last thing I will leave you for the thought problem. We have a flow like this. Flow of water down an incline. Very similar to the previous one, but now this is down an incline. I will not solve the problem right now. I will leave it for you. You people should think maybe it will be solved in the tutorial, but or in the next class. Next class, the thing is the next lecture comes on next Thursday. Monday we have the quiz. So therefore, I'm preparing you for the tutorial. Now, what is the difference between this problem and the previous problem? Again, if we assume steady flow, fully developed, all those assumptions, one thing is the gravity now will have components in both x and y. So one of them will be g cos theta, other will be minus g sin theta, or whatever, you work it out. Other things are same. What are the boundary conditions on this problem? At y is equal to 0, what is the velocity? Vx and Vy are 0. At y is equal to h, if we assume that this is h, what are the boundary conditions? Y is equal to 0, Vx is equal to 0, Vy is equal to 0. What are the boundary conditions on y is equal to h? This is air on the top, water at the bottom. So the boundary conditions will be, firstly, P is equal to P atmosphere for all x, and because this is a liquid gas interface, shear stress there will be 0. So you will now, because of pressure, now pressure and gravity are there in both. So you will once again get Vy is equal to 0 from continuity equation. Now when you from Vy is equal to 0, you solve for pressure, and you will get a pressure distribution as a function of x and y. And now partial P by partial x will not will also be 0, or it will not be 0. You work it out. You work out the boundary condition, equate the partial P by partial y, and get pressure as a function of y. And then you go to partial P by partial x, the x equation. Okay? And in fact, partial P by partial x will turn out to be 0. It was not 0 in the previous problem. In this one, because at y is equal to h, P is the same for all x. So it will turn out that it will be 0, but it will comes out from the equation, not by this physical logic. And then you solve. Now, again, if you try to look physically at the equation in the previous problem and this one, acceleration will become 0. What is acceleration? The left-hand side of the equation. That is 0. And what we have is a balance. In the first case, there was a balance between viscous flow, viscous terms and the pressure gradient. Here what you will get is there is a balance between gravity and the viscous term. So you solve for this and you will be able to try to solve it. I think you'll find it interesting and get the answer. Okay. So I think पिछली बार निग्लेक्ट नहीं की थी, वैसे रहती तो भी सेम रहती. वो निग्लेक्ट इसलिए की थी कि P1 और P2 जो स्पेसिफाई किए थे, either I should have specified them as function of gravity, but because I've treated them as constant, so what, that is why in that sense इसमें नहीं, इसमें gravity neglect नहीं होगी. इसमें answers will be a function of theta and gravity. So you have to assume this angle is theta and gravity is like this. Here the pressure gradient will be 0. Partial B by partial X will turn out to be 0. There everything was a function of P prime. In this problem it will be gravity which will create the viscous gradient or whatever. Okay. So this I have not solved for it, but you will do it. In the next class I will take one circular problem. The pipe flow exact solution. I will take one of the circular versions and then we'll move. Okay. You can also try, इसका भी homework load कर दिया है, बाद में उसको भी try कर लेना after the quiz. उसकी मैं देखेंगे उसको सबमिशन का. उसमें ये नहीं लिखा था दोनों को सबमिट करना है, एक ही को करना है. असाइनमेंट 10